On the first section, we did 5.4 part 1, and it was getting kind of long, so I stopped. And I just finished, boy, now I'm trying to remember, this is not good. Okay. Oh yeah, we did that one. We did that one. We did that one. All right. So, sorry, it took me a minute there because that was yesterday. Today's a new day. So last time I went through this whole thing here and explained why each of these are true. And now it's time to work some examples. This first one, so okay, it says identify the zeros. So to identify the zeros, you make the numerator equal to 0. And we're going to need to factor that. Oops, x plus 3, x minus 2. Okay, so set those equal to 0 and you get negative 3 and 2. Those are the zeros. The vertical asymptote is when you make the denominator equal to 0, as long as there's no common factors. We haven't talked about that yet, but that is the case. So if you make the denominator equal to 0, you get x equals 0. That's your vertical asymptote. That's a line. And then we get to talk about the horizontal asymptotes. Oh, here's my little list right here. So the zeros are negative 3 and 2. Vertical asymptote, x equals 0. And then the horizontal asymptote is where we consider that one of the three cases. So on this one, you look at the top, the degree is 2, and on the bottom, the degree is 1. So the top has a higher degree. That means as x gets really large, the top is going to get large faster than the bottom. So you're going to have a large number divided by another number. You're still going to get a large number. So in other words, it never flattens out, so there is no horizontal asymptote. You can also simply memorize this table over here, and you can see that it's this one right here. Now it says to graph all this. Zeros, negative 3 and 2, so I'll put some tick marks on here. Here's negative 3, here's 2, those are my zeros. Vertical asymptote, x equals 0. Let's go to a different color so we can see it, because it's going to have to go right on that axis. And there is no horizontal asymptote. So that means it's not going to level off. So it probably is going to do something like it could go like that. It might go like this. It's hard to tell without graphing more points. So if you had to do this problem by hand, you would make a T-chart, and you would choose something to the left here like negative 4, negative 5, negative 6 if you really wanted to do a good job. You already know negative 3. I would choose negative 2, negative 1, and you need to choose 1 because you need to know what it's doing in here. And you would choose these points out here. To save time, sure, I could plug each of those in and plug and chug and get all these y values. To save time, I'm just going to do it on the calculator. Just keep this video somewhat shorter. Remember again, when you're putting these in, you have to put parentheses around the numerator. And, whoops, that's not supposed to be there, it's supposed to be divided by the denominator. In this case, we don't need a parenthesis because there's just an x. Zoom 6 for a standard window. Okay, so it turns out it looks like that. So sure enough, we knew this was an asymptote, so we know it's approaching, and then this is going to go that way, and then, let me look at it one more time. Okay, so this one gets pretty close up in here, and then it kind of goes like that. Next. Letter B. And if you want, you can pause the tape or the video and try it on your own. So zeros, I'm going to set the numerator equal to 0 and solve. I could actually do that in my head. I can see that that's 1. So 1 is the 0. Vertical asymptote, I'm going to set the denominator equal to 0 and solve. There's only one solution on that one. It's 0. So again, it has a vertical asymptote at x equals 0. And on this one, the denominator has a higher degree. So that means the denominator is going to approach a bigger number faster than the numerator. Usually I just kind of think about it as 1 or some number up there. So you're going to have some number divided by a really large number. That's going to be a really tiny number, close to 0. So that means the horizontal asymptote is y equals 0. If I think through it this way, I don't have to memorize this little chart down here. And then I am going to move my chart because I want a graph here. We want to try to do as much as we can without memorizing. That's my motto. Because if you memorize, you might forget it. But some things we have to simply memorize because we use them, especially if we use them a lot. Like the area of a circle. Things like that. So we have a 0 at x equals 1. We have a vertical asymptote at x equals 0, so I'm going to change colors so we can see that on here. And this time we also have a horizontal asymptote at y equals 0. So that's this line here. Now isn't this interesting? This graph actually crosses the horizontal asymptote. And that's okay. Graphs can cross asymptotes. They just have the graph just has to approach the line. So this is a very interesting one actually. Okay, let's look at it and see what it looks like on a calculator just to save time. It's faster than graphing by hand, as you know. I'm not even too sure what this one's going to look like, so let's find out. Okay, so in the numerator we need x minus 1 divided by, and then x squared does not need parentheses. Let's see what we got. Oh, look at that. Aha, this is a very interesting one. So what it's doing down here, you can't see it very well, so I'm going to change so that you can see this better, I'm going to change my y max to maybe 2. Maybe even just 1. Let's try that. Okay, there you can see it. What it's doing is it's coming up and crossing, but then it's going to have a max, it's going to maximize, and then it's going to drop back down again. So it's kind of going like that. And then I already forgot the other one, can you believe it? Okay, and then this one is just right in here. Well, they gave us a really interesting one. This is not a typical parent function, so I was not familiar with this particular one. I do know, though, that they can cross horizontal asymptotes. That does happen. But notice how when the whole thing is when x gets large, as x approaches infinity, the y is still approaching 0, which is what we would expect. Also notice as x approaches negative infinity, the y is also approaching 0. So on both ends, it's approaching y equals 0. That's why the horizontal asymptote is y equals 0. Well, let's see how this one is. Zeros, we set the numerator equal to 0 and solve. I'll just go ahead and do the steps. I was going to do it in my head, but I see that I can factor out a 2. I see that this is a difference of squares, so that's x, 1, plus 1, and minus 1. And when I set each of these equal to 0, the 2's not going to give me any solution, so I just ignore it. This is going to give me negative 1 and positive 1. So those are my zeros. Vertical asymptote, set the denominator equal to 0. So my denominator is x squared minus 4. One way you can do this is you can factor like so, and then we see that the solutions are plus or minus 2. The other way you could have done it is added the 4 across and taken the square root. You have to be careful though, because if you forget the plus or minus, you're just going to get 2. But really it should be plus or minus, because as we saw up here, we got 2 solutions. So there are actually 2 vertical asymptotes. X equals 2 and x equals negative 2. And that's okay too. That happens as well. That's perfectly normal. Horizontal asymptote. Okay, look at the degrees. We've got an x squared and an x squared. They are equal. On this one, you take the coefficient, the leading coefficient, there's a 1 there. The 2 over 1 is going to be the horizontal asymptote, y equals 2 over 1, or y equals 2. That one is just easy to remember. That's this last one right here. Now we got this whole thing to graph, so we've got lots of room. We'll graph the information we know, and then we'll fill in the rest with the calculator's help. I think that's a nice compromise. So we've got zeros at negative 1 and 1. We've got vertical asymptotes at x equals 2 and negative 2. I like to use a different color. Oh, yellow, that's fun. There's 2 and there's negative 2. Wow, those are kind of interesting colors together. And then a horizontal asymptote at y equals 2. So you could try to guess what this looks like. Really all you can, well, you know it's not going to be down in here anywhere because there's no zeros. Here, if it has to be continuous, it's probably going to have to do something like this. Oh, guess what? We could try when x is 0. If you plug 0 in here, you're going to get 0 minus 2, so you're going to get negative 2 on top. 0 minus 4, negative 4 on bottom. That equals 1/2. So we know that it has a y-intercept of 1/2. So this part of the graph I pretty well can guess is going to do this. Kind of like, it looks like a parabola, doesn't it? But it's really part of a greater graph. I know that there's no branches down here because if there were, they would have to cross the x-axis, and we did not. We only have these 2 zeros. So I'm guessing my other 2 branches are probably up here like this. So let's check it on the calculator and see. Clear. Remember parentheses around the numerator. 2x squared minus 2 divided by parenthesis. Very important to put those parentheses in. X squared minus 4. Let's see. Let's do a zoom 6. Ha! I was right. Of course, I've done a few of these before. Notice here is y equals 2. So these, this curve is approaching the asymptote. It's getting pretty darn close to it right here, and it's getting really close to this other one here. So it looks like this and like this. That one was kind of fun. Here are 3 to try on your own. And what I will do to save time is I will just give you the answers. And if you have any questions, please ask during class and I would be glad to help you. Okay. So if you have the time, take the time to try these on your own. Okay, I'll admit it, I am just going to copy the answers straight out of the book. So for A, according to our book, the zeros are negative 5 and 3. Asymptote, it only has a vertical one at x equals 1. And then when you graph it, this part 1, 2, 3, 4. It's easiest if I just do it 1, 2, 3, 4, 5. 1, 2, 3. We have a vertical asymptote at x equals 1. So that's the information we got from our algebraic analysis. And if you look at the graph, it goes, well, it kind of bends out there. And this one comes way up like that. So that's the first one. The second one, the zeros, oh, there's only 1 0 at 2. We have 2 vertical asymptotes, x equals negative 1 and x equals 0. And the horizontal is y equals 0. When you're listing your asymptotes, again, please write the entire equation. Don't just write negative 1, 0, and 0. I have no idea what that means. I need the lines. Okay, we'll put all this on a graph. Going kind of fast so I don't take up too much of your time. 0 at 2. Vertical asymptote at negative 1. And, oh, I need another color because it's right on the axis. Ooh, skinny there. And then we've got a horizontal here at y equals 0. Back to this beautiful purpley color, rust color. And it looks like, from what we've got here, that's interesting. It has a 0 at 2, but in the book, I'm going to graph this one myself. I've got to see this for myself here. Parenthesis around the numerator, divided by parenthesis around the denominator. Zoom 6, it's already on. I've got a This is interesting. I can't tell what's going on here because it's so close to the axis. So I can see what's going on here. Okay, I've got this branch down here. This, by the way, is my vertical asymptote on my calculator. It doesn't show it as a dashed line. It shows it as a straight line. There really is not a straight line there. Whoops, gets a little closer. And honestly, I can see a little tip of a graph up here. Let me go to my window and make my Y max bigger for a second to like 20. Okay, see, I can see there's a little thing right here, way up there, so I'm just going to kind of graph it in there. This is not drawn to scale. If I had more time, I was going to take more time, I would draw the, it's actually up at 10. So this is really supposed to be somewhere around 10. You can look on you could trace, I suppose we could do that. Just to see, whoa. So yep, around 10 is where this thing has a minimum. But whoops, what I'm really interested in, come back, is what's happening down here. So I want to make my Y, I'm going to make it from -1 to 1 so I can really see what's going, so I can see what's going on down there. -1 to 1, maybe then I can, look at that. It's crossing at 2, well wait, 1, 2, it looks like almost that just doesn't make sense. Oh, that's my axis. Okay, this is the x-axis right here, or the y-axis. Sorry, I'm getting all twisted around. Here's the axis. Here's the asymptote. Here's 1, and then this is 2. So it's crossing. It's coming up, maxing out, and then coming back down, but it's staying on top of the x-axis, like that. It's a tricky one. Okay, enough time spent on that one. Let's check out this next one. 4C. The zeros are -1/3 and 0. The asymptotes are, I'm just going to list them, x equals -3, x equals 3, and y equals 3. Let's throw those on a graph. We've got a 0 at -1/3, that's about there. Oh, and 0, oh my goodness. Look at the problems they give us, so skinny. And then I'm going to go to my yellow. 1, 2, -3. X equals 3, 1, 2, 3. And y equals 3. This thing must just come just right up here and come like that is my guess. And I'm guessing there's a branch here and a branch there. Let's see what we get when we graph it on the calculator. Okay, clear. Parenthesis around the numerator. Divided by parenthesis around the denominator. And graph. Oh, I want it so I could see that one, sure enough. Let's graph that in here. And I have to go to a different window so I can see what's going on up here. So I'm going to go back to my Zoom 6. And then you can see here's the horizontal line, y equals 3, that these two branches are approaching. Notice my vertical asymptotes on my calculator look like solid lines. They are really not. They're really dashed. It's just the limitation of the calculator. The 84s probably don't have those lines in there for the asymptotes. Okay, good, we did it. Let's move on. Okay, now we get to talk about holes. Holes happen when you have a common factor on top and bottom. So, common factor on top and bottom, so on numerator and denominator, I'll say on top and bottom, will result in or produce a hole in the graph. It's a gap in the graph. So this is a perfect example. F of x equals, so on the top I've got x squared minus 4. Let's go ahead and factor that. We've been working with these quite a bit, so hopefully you all know that that's how that factors on top. And notice that we have a common factor here. These cancel, right? So this f of x, which is this whole thing, looks like g of x, the simplified version of x minus 2. What's x minus 2? That's a line, right? It's a line. So, let's check this out on the calculator. When I graph the original one, let's graph the original f of x and see what we get. Close, so parenthesis, x squared minus 4, close your parenthesis, don't do that, come back, hit the wrong button. Okay, close your parenthesis, divided by parenthesis x plus 2. Let's hit graph. Look at that, a line. Just what I thought, because I simplified it and I got a line. So this, even though it looks really complicated, is really just a line. However, it is not a solid line. It is not continuous. It has a hole. And the hole is where the common factor equals 0. So x plus 2 is common to top and bottom. What you're going to do is set that equal to 0 and solve. And at x equals negative 2, I have a hole. And I knew that. You kind of know this because remember when we checked to see where it's undefined, this function would be undefined at negative 2, right? You can't have a negative 2 here. So sure enough, if it's undefined at negative 2, that means there can't be a y value for negative 2. Let's trace and see. Of course, let's just look at the table. That'll be easier. So on your table setup, I'm going to start at, actually, let's start at negative 2. No, negative 2. Second table. See how you have a y value everywhere, but at negative 2 there's an error? So that indicates that there's a hole there. When I go back to my graph, I can't see the hole. You would not know it was there unless you did an algebraic analysis like I just did here. So this is where the person is smarter than the calculator, at least smarter than this screen on the calculator. Okay, so the holes, you would say x equals negative 2, you would mention that there's a hole there. Oh, by the way, if you were graphing this by hand on a, on a piece of paper, how do you indicate the hole? Well, what you would do is you would graph the line x minus 2, so I know it has a y-intercept of negative 2, it has a slope of 1, so it looks like this. I would go ahead and you would draw the line, and then when x is negative 2, here's x equals negative 2, you would come down where it hits the line, you'd put a little hole like that, a little open circle, and that means that there's a hole there. So g of x, this line and this graph are the same everywhere except at negative 2, because on this line it would include negative 2, and on this one it does not. So this is a little thing in the book says, common factor x minus b in both the top and the bottom, then there's a hole where x equals b. Unless the line x equals b is a vertical asymptote. You know, if there's a common factor on top and bottom, it's not going to be a vertical asymptote, it's going to be a hole. That's why if you do, let's go back to this. If you do have this sort of situation and you say that there's a vertical asymptote at x equals negative 2, you will be wrong. There is no asymptote, no vertical asymptote at x equals negative 2. So when you're finding vertical asymptotes, you have to be careful and make sure that there is not a common factor in the top and bottom, because that will produce a hole instead of an asymptote, a vertical asymptote. So, like this problem right here, I wouldn't be able to just come along and say that there's a vertical asymptote at x equals negative 2, because there might be a common factor. So let's see if there is. Let's go ahead and factor f of x. I know the bottom is x minus 2, and I'm going to have, positive 3 and negative 2, right? Sure enough, there's a common factor here. So that means there's going to be a hole, not a vertical asymptote, at x equals 2. When you cancel those out, you get g of x equals x plus 3. So the graph of this is this line, but with a hole at 2. So if I want to graph that, I can do it pretty quickly, because this is a fast line to graph. It's just the y-intercept of 3. and a slope of 1. Up 1 over 1, down 1 over 1, and it's going to cross over here, 1, 2, negative 3. This is what f looks like, but f has a hole at x equals 2, so I have to go over to 2 and then come straight up until I hit the line. Right there is a hole. So this is f. I'll confirm that on the calculator. Y equals clear, parentheses around the numerator. Always graph the original one, not the factored one, in case you made a mistake. And then parenthesis around the denominator. Graph. Okay, does that look like mine? Yes. Notice on the calculator, you're not going to see that hole, but if I go, another way you can check it is you can go second trace value, and since I know I have a hole at 2, I can put 2 in, and see when I do that, y is blank, meaning there's nothing there. So I put a hole there. Oh, this will be our warm-up. Now, I'm actually remembering the joke. Whoops, I went too far. Oh, here it is. What's the difference between a golfer and that function? One gets a hole in 1, and the other has a hole at 1. And see, now it makes sense, because if you factor this, notice, common factor, you're going to have a hole when x equals positive 1, because you set the common factor equal to 0 to get the hole, so there's a hole there. Okay, we're done.